Hi, in this video, we want to keep on looking at introductory statistics with Python. Specifically, we're going to look at some categorical data tests. So we're going to be looking at some hypothesis testing that's specialized for categorical data, that is qualitative data. All right, so we're using this textbook, an Introduction to Statistics with Python. It's through Springer. Here is the website for the code that I'm using right here. And remember that if you're a UCF student, you can use Springer Direct to download this textbook. I think it's a good book to be going with if you're going to be getting into data with Python, because introductory statistics will be more familiar to you than other aspects of data. If you've taken like an intro to stat class, if you've done means and standard deviation, stuff like that, this will definitely kind of bridge some gaps for you. All right, so we're interested in analysis of categorical data. First, we're going to look at how to analyze binary data if we're interested in analyzing the proportion of success or failures. Then we're going to look at analyzing tables of counts. And so when I talk about a table, that's a rectangular table of numbers. Then we're going to look at a special test that is for 2x2 tables of counts. Then we're going to look at the situation where we have like multiple judges and multiple subjects, or multiple tasks and multiple subjects, some way that there is like an evaluation going on, and we have subjects, we have multiple subjects and multiple ways that they're being evaluated. And then we're going to finish it off with analyzing paired categorical data. All right, so let's go ahead and load our packages. I'm pressing F9 in Spider to get these to come in. So I'm getting NumPy, and then I'm getting PyPlot from Matplotlib, and I'm getting SciPy stats. All right, so now we want to look at analysis of one proportions. So what we want to do on this one, we want to calculate the confidence interval of the population where we have binary data. Okay. So anytime that I've got two possible outcomes for my observations, what I can do, I can say that one of the levels corresponds to a 1 and the other corresponds to 0. And that way I have some advantages with that. For example, if I take the average of those 0s and 1s, that tells me what proportion is at the level that corresponds to 1. All right, that's nice. Well, also, the moment I do that, we can take advantage of the binomial distribution. And if I have the binomial distribution and I start taking averages, then through the central limit theorem, I can use the normal distribution to give me more information about those proportions. All right, so that's a lot of words. That's a lot of words I just said. Basically, what I want to be able to do, I want to calculate a proportion, and I want some feedback on how precise my estimate of that proportion is. All right, so what we do in statistics, we do something called a confidence interval. If I have a very wide confidence interval, it's like super wide, I have very little precision. I don't have very much confidence in the precision of the estimate that I have. But if I have a really, really, really tight confidence interval, it's really, really small, then I'm very confident about that the correct measurement is inside that width. So what we want to do, we want to come up with an interval of numbers that gives me some feedback on how precise my measurement is. How much confidence can I put into my measurement? All right, so in this story problem, suppose that there's a general practitioner that chooses a random sample of 215 women from their patient registry, and they find that 39 of them have a history of suffering asthma. And so what is the confidence of the prevalence of asthma in his sampled population? All right, so something about this is that when you talk about this, we always have to consider what is the sample population. His sample population is his patient register. So compared to the general population, it's probably going to be a bigger number than the proportion of the population as a whole. Something to think about when you start making your interpretations of your outcomes. All right, so let's go ahead and get the data. So here we got number total is 215, and the number of positive is 39. So now let's go ahead and calculate some confidence intervals. So first and foremost, I want to know what is my estimated proportion of patients in the registry with asthma. So it looks like it's about 18%. Okay, now it might be that I missed a few. Maybe there was a misdiagnosis along the way. Maybe some of the patients were diagnosed as asthmatic when they weren't. Maybe they should have been diagnosed as asthmatic, but we didn't. So we need to we want some idea of how close to this correct proportion do we have. All right. So what we're going to do, we're going to use some tricks in mathematics that gives me a way of estimating what is the standard deviation of this estimate. All right, so standard deviation of an average is called the standard error. Okay, standard error is the standard deviation of some kind of measurement, but we call it standard error to specify what that's a special type. Okay, so I've got binary data, I've got two levels. So in reality, I'm dealing with the binomial distribution. Now, the binomial distribution is kind of difficult to work with directly. We could brute force, so we can work through this, but it works out that if I look at the central limit theorem, anytime I'm taking an average, I can take the normal distribution. That is the bell curve, also called the Gaussian distribution. So, it's got a bunch of names because it's so important, and this is why it's so important. That anytime I start doing sample averages, I can invoke, almost always, I can invoke the normal distribution instead. That standardizes things so I know how to handle things every single time. Okay, so what we're going to do is I'm going to get the standard error that the central limit theorem gives me for a binomial problem like this. Let's go ahead and calculate that. So the variance of binomial distribution is n times p times 1 minus p. And if we do a little bit of adjustment, then we see that it's going to be, the standard error is going to be p times 1 minus p divided by the total number. Then I take the square root. And that tells me my standard error for what's going on. All right, so what do we get for a standard error? All right, so this is 0.03 about. So my point estimate is about 0.18, and my standard error is about that. Okay, so what this is telling me what is the estimated proportion of asthmatic patients in the register. And now this is giving me an idea of it. So if this was a really big number, so let's say that this was like 0.9. If this was 0.9, I would not have very much faith in this number as an estimate, because 0.9 is a huge number in terms of numbers that go from 0 to 1. Now, if it was 0.000001, then I would be very confident that I have a good estimate in this value here. And 0.03, that's not too bad. So what we want to do now, we want to go ahead and figure out what is the actual range of values that I can be 95% confident that the correct estimate is within. So what we're going to do, so remember that we're going binomial distribution. Central limit theorem gives us normal distribution. The normal distribution, we don't know everything about, so we use the t distribution also. So I mean, there's kind of a chain going on here. You'll notice that at this point, I'm invoking the t distribution. All right, so what do you need to remember going forward? If I'm doing binomial stuff, if I want to be able to do these calculations, I'm going to actually use the t distribution instead of the binomial distribution, instead of the normal distribution. That fills in some gaps for me. Okay, so let's go ahead and hit this. Now let's go ahead and execute that. Okay, so this is a whole bunch of stuff going on. So here we're figuring out, we're using the t distribution to figure, to figure out what values are there to be kind of spread out for us. And then we're rescaling it because the standard error tells me like my level of precision. I need the distribution and my understanding of precision mixed together to come together to give me an idea of how spread it actually is. Now here, this is just plus or minus 1 when I'm adding, -1 when I'm subtracting. And so this, I'm taking my estimate, whoops, please read my mind. Okay, I'm taking my estimate. I'm going to take the 1, I'm going to add all of this to get the upper bound of my confidence interval. And then I'm going to, so that's going to be the bigger value in the confidence interval I'm about to look at. Now I take my estimate and I subtract this value to get the lower value. So I'm going below and I'm going above to get an interval around my estimate. All right, so what does that look like? All right, so we can see about 0.13 and we can see about 0.23, something like that. All right, so what this is saying is that we are 95% confident that the true proportion of patients in the registry with asthma is between 0.13 and 0.23. Okay, I mean that's a range of 10%. Now, you know, we can be pretty certain that the true proportion is less than 1/4 and greater than 0.1, right? So it's definitely between like 10 and 25%. So that gives us an idea of what's going on. Now, it is possible to get a negative value on your confidence interval for this. Anytime I get a negative value for a proportion that doesn't make sense, I replace it with a 0. If I get, for the upper bound, a value greater than 1 that doesn't make sense, because a proportion greater than 1 does not make sense, I reduce it down to 1. All right, so now let's go ahead and take a look. What do we have for actual confidence interval? All right, so from 0.13 to 0.233, we are 95% confident that the true proportion is between those two values. All right, now something that's kind of weird about statistics is that we always have to say, I'm 95% confident that the true value is between these two values. Why do we have to do that? Well, if I'm 100% confident, I have to go 0 to 1. If I want, to be honest with you, to have 100 full complete confidence in something, I have to make it something so ridiculous. I have to make a ridiculous statement that is not informative, that for me to be truly 100% confident. When I say I'm 95% confident, what I'm doing, I'm shaving off the extreme 2.5% on the right and the extreme 2.5% on the left. I shave off the extreme values and I just look at what's in the middle. And that's why we do a 95% confidence interval. So we kind of balance some aspects. This is a weird way of thinking. And honestly, in my experience when working with decision makers who do not have a stronger statistics background, and even when they do have a decent statistics exposure, they don't want to think in confidence intervals and they don't want to think in p-values. P-values they might accept. Usually my experience is that if they know the problem, they know the estimate, and they know the sample size, usually they intuitively know what that standard error aspect, what the spread is going to be. So intuitively, they kind of figure out what the value of an estimate is. So it's, in my experience of presenting to people, it's what you should do. You should give the point estimate and then keep the confidence interval and the standard error like in your back pocket, ready to pull it out if they start asking such questions. Otherwise, you should just not even bring it up, because if you start going down the rabbit hole of statistics, most people are going to zone out on you and it isn't worth it. All right, next we want to talk about the chi-square test. All right, the chi-square test, what we're interested in is we want to look at tables of counts. All right, so let's say potentially I could have a 3x4 table of numbers, and the numbers represent a count of how many times something happens. Okay, and each row and each column correspond to different values of two different variables. And so here we're going to just do a 2x2 table just because that's simple. It's a good place to start. All right, so let's go ahead and take a look at OBS. So here we've got 32, 118, 17, and 127 are the values. And what we want to do, we want to see, is there statistically a difference between these, like somewhere, is there a difference within a cell anywhere from what we would expect to see? So what's going on is that we can figure out if I was to tell you the sum of the rows and I told you the sum of the columns, and you would be able to figure out what is like the average for each individual cell. Okay, so if we see if the value we see inside a cell is far away from the average that we would expect, then we know that using rows and columns is not sufficient to model the distribution of these numbers. Okay, so in that case, that is going to be a reject the null hypothesis. The null hypothesis is that the rows and columns information is sufficient for telling me what's going on inside that table. And the alternative is that that the counts deviate from what the rows and columns rows and column sums tell me. All right, so here I can see that I would have what, 150 if I add these two together. Here I could see that I would have what, 144 if I add them together. And down here we see that we would have a 49 and we would have 145 if I add these columns together. And we can figure out that if everything is just kind of like evenly distributed how we would expect it by just looking at the column sums and the row sums, we can figure out what each value would be on average on the inside. If the values inside deviate from that average that we expect, then we reject the null hypothesis. Okay, so that gives, and if I get a big value from the chi-square test, so if I want to do my calculations, if I get a larger value, I'm going to be leaning towards rejecting the null hypothesis. If I get a smaller value, then I will think that the marginal value, the marginal distributions corresponds to the internal distributions. All right, now when we do chi-square test on 2x2 tables, there's something called a Yates correction, and that addresses the fact that we have some coarseness in our tables when we approach this. Honestly, most of the time you start talking about correction values. If a correction changes your conclusion, you know that you're on the borderline of where you want to be, and you can't really be firm. Like don't fully trust your conclusion if a correction term changes. Adding or removing a correction term would change your conclusion. Don't have a whole lot of faith in your conclusion, honestly. All right, so let's go ahead and take a look. So let's compute it. We're doing a chi-square test. All right, so if I do the corrected value, we get 4.141, and our p-value is 0.04. And if we do uncorrected, we do 4.8 is our chi-squared value. So if the value here is big, I'm leaning towards rejecting the null hypothesis. I will conclude that the marginal is not enough. The rows and column information is not enough. Here, the p-value is 0.03. Okay, so I've got 0.03 and 0.04. That's not a big difference. I mean, of course, there's going to be a difference in the calculations. So, that's close enough that these are consistent with each other. And so either way, I'm going at the 0.05 level, I will reject the null hypothesis in favor of the alternative. Next, we want to look at Fisher's exact test. All right, so Fisher's exact test, once again, we're looking at 2x2 tables of counts, but now how we calculate the value is different. So previously, when I did the chi-square test, I had two different ways, corrected and uncorrected, for calculating. Now I'm pulling out a third way. Now this Fisher's exact test, usually this is only done on 2x2 tables. Like R can handle more complicated cases, but if you read the textbooks, I've only seen the 2x2 case worked out. And I don't know really what Python does. Usually if we go something other than 2x2, we go to the chi-square test instead. And largely we do that just because that's what people are expecting. And the chi-square test tends to be like your default go-to for most categorical hypothesis testing anyway. All right, so we want to look at spectacles for juveniles and non-delinquents who failed the vision test. And we can see that in the data, we've got one delinquent that wears glasses. We have 5 non-delinquents that wear glasses. We have 8 delinquents who do not wear glasses and 2 non-delinquents that do not wear glasses. All right, and what we want to know is there a difference in these two populations? Do we see spectacle wearing evenly between the two groups? Do we see delinquency evenly among the glasses and non-glasses kids? All right, so let's generate our table of numbers. So we got 1, 5, 8, and 2. And how we actually compute this next part is using some combinatorics. We're using the nChoose2, or sorry, not nChoose. We're using the choose function to calculate what we want. All right, so let's go ahead and take a look at the output. All right, so the probability of obtaining a distribution at least as extreme as this one that was observed, assuming that the null hypothesis is true, is 0.04 about. I just read this off. Okay, so remember, if I have a small p-value, I am leaning towards rejecting the null hypothesis. So this is below 0.05. So I'm going to reject the null hypothesis in favor of the alternative. All right, so the null hypothesis on this one is that spectacle wearing for delinquents and non-delinquents is equivalent among the two populations. Or we could say that being a delinquent among the spectacle and non-spectacle populations is equal. Here, we reject that statement. So we conclude that there is something going on. Now what, we don't know. If you look at the mathematics of this test, it doesn't matter if we're looking at spectacle wearing among the populations of delinquent and non-delinquents, or if we look at delinquency with respect to the populations of glasses, non-glasses. So the interpretation is, there are two different interpretations of this. The statistics works out to be the same either way we approach it. So remember, I'm approaching there's two different ways to phrase hypothesis testing on this. So when we approach this, you need to make sure that you get the variables worked out very clearly. All right, next we want to take a look at the Cochrane's Q test. All right, in this situation, we have multiple subjects and they're going to be evaluated in multiple ways. They're going to be measured in multiple ways. And so it's possible, so think about, maybe we're talking about like ice skating. And we have ice skaters going out. And each of the judges have different criteria on what they call good and bad ice skating. Now, so we have different subjects. Each subject is going to be a different column, and each judge is going to be a different row. And what we want to do, we want to know, is there a difference among the subjects? Is there a difference among the judges? We're interested in this. Or do we conclude that everything's all evenly distributed? All right, so what we're going to do, we're going to take stat models, sandbox stats, run, and we're going to import Cochrane Q. And now we're going to get pandas. So now let's go ahead and generate our measurements. Okay, so here there are 3 tasks that each subject is measured on, and each subject corresponds to a different column. There's 12 different subjects. Now, the author of the textbook, he prefers to have it in the form of a data frame, and I can totally see why, because I prefer it in a data frame, because it makes more sense to be saying that we've got task 1, 2, and 3, and then I would have gone ahead and I would have labeled these as subject 1, subject 2, and so on, but whatever. All right, so now let's go ahead and let's drop our data frame into Cochrane's queue. And notice that I've got this notation of parentheses and a comma in between. So I'm picking up the Q statistic and the p-value. The Q statistic, what we're going to do, we're going to compare this to a special chi-square distribution. And by doing that, we're going to get a p-value. So remember that if I see that I have a small p-value, I'm going to be prone to rejecting the null hypothesis. Okay, the null hypothesis is that everything is equal. Well, here at 0.01, I'm pretty sure that it's not all equal at this point. All right, so we conclude that there is a statistically significant difference between the 3 tasks. Now, what is that difference? I don't know. I need to go into the original data and start, combing through it with a fine-tooth comb to figure out what's the difference there. My first way of doing that is I would look at the average of each task. So, I mean, just eyeballing this, we can see that the third one has a total of 2 values that are 1, and then the others have more. So I would, just eyeballing it, I would conclude that the third task is much harder than the other 2. Now we want to look at Neymar tests, or sorry, McNeymar tests. Or in this situation, what we want to do, we want to look at the situation where we have paired categorical data. That's really, whenever you see paired categorical data, so I have a subject before treatment, subject after a treatment. So the same person before and after. If I can match like the before and after aspect, or the brother and the sister, or we're talking about twins, something like that. If I can match different subjects from different aspects of the test, it's probably a paired test. All right, and this is one of the classical examples for this. So a researcher attempts to determine if a drug has an effect on a particular count of individuals that are given in a table. The researcher attempts to determine if the drug has an effect on a particular disease. We've got counts of individuals in a table with a diagnosis. So before treatment is in rows, and diagnosis after treatment is in columns. And so remember, because it's paired, the test requires the same subject to be included in the before and after measurements, that is, it's matched pairs. All right, so let's go ahead and do this. So once again, I'm taking stat model, sandbox, stats, run, and I'm going McNeymar. And here is my data. So let's go ahead and get our test statistic and the corresponding p-value. And so we use a special chi-square distribution, the statistic to figure out what is the p-value. All right, 59. If I have a big value, I'm prone to rejecting the null hypothesis. And now I get the p-value. Wow, that's a small p-value. I mean, that's pretty small. So I'm going to end up rejecting the null hypothesis. I know that there is a difference going on. So my conclusion is that there is a significant change in the disease by the treatment. All right. And that is all I've got for you. I hope you're enjoying the course. I hope you're staying healthy. Take care and goodbye.